We are the students of Aditya College of Engineering and Technology from the Department of CSC, Internet of Things. We are from Batch 4 and the title of our project is Advanced Arduino-Based Stress Analysis for Chronic Fatigue Syndrome, which is basically an integration of the technologies Internet of Things and machine learning. My name is Swathi Priya and I am basically responsible for data collection and processing in the project.
I am Prem Kumar. I am responsible for developing the ML model using random forest classifier for classifying the stress levels of a person.
Hi, myself Bharath, and I am responsible for the connections in between the sensors and the Arduino board.
Hi, myself Sahithi. My role is statistical validation.
Hi, and now I'm going to explain the hardware connections of this project. This is the display, LCD display, and here are the 4 pins. One was ground and second one was voltage, and last two are the clock sensor, clock line, and also data line, serial clock line and serial data line. These all are connected to here. Serial clock line was connected and serial data line, and as well as this brown wire has been connected to here to the ground, and this red line voltage was connected to here is 5 volts. And after that, this orange wire has been connected to the buzzer, which is the pin of 9. And can you please come here? Yes, here it is. This 9 one was connected to the buzzer over here, and after that there is an yellow wire connected to the LED, which was red light, which indicates the danger, and green wire was connected to 7, and which indicates the normal thing. And after that this is a BMP sensor, and also this is an heart rate sensor, which is connected, this is connected to here, like voltage and ground. So after that, the data which is collected will use this Arduino board, which heart rate sensor was connected to A2, and this is a galvanic sensor. This sensor uses the skin response, and also heart rate sensor will calculate the heart rate and pressure, and this will calculate the temperature and all. So for now, this galvanic sensor was connected to AO, like A0. Here we can see, and after that A4 and A5 are connected to BMP sensor, which is used for temperature thing. Thank you.
So today I'm here to present my final year project titled Advanced Arduino-Based Stress Analysis for Chronic Fatigue Syndrome. This project aims to help in the early detection and monitoring of chronic fatigue by analyzing physiological signals using a combination of hardware sensors and machine learning. The system integrates real-time sensor data acquisition through Arduino, performs live data logging, and uses a trained random forest model to classify stress conditions as normal or abnormal, providing immediate visual and audio feedback to the users. So currently we are going to look through the code that we have implemented. So the first code we have is for making a serial communication with the Arduino and trying to read the input values using the different sensors we have. So as we can see in this code, so the first thing is that it establishes a serial communication with an external device, but before that it has also imported important modules like serial and time, and also the COM port is specified, which is COM8 in this case, and the baud rate is specified, which is 9600 in this case. So now the code begins by importing the necessary serial and time libraries. It then specifies the COM port and the baud rate for communication as mentioned previously, and using the Pi serial library it opens a serial connection and waits for 2 seconds to ensure proper initialization. Inside an infinite loop stated by while true, the program sends the character A every second to the connected device. It then listens for any incoming data. If data is available, it reads a line, decodes it to UTF-8 if necessary, and displays the received message. Exception handling is included to gracefully manage serial errors and keyboard interruptions. finally, the serial connection is closed when the program exits. This script enables two-way communication with a hardware device, making it ideal for real-time data exchange and control. So next up, we have another Python script which is basically used for reading the sensor data and then storing it in an Excel file for further use. So it sends a signal to the Arduino, receives a data string containing values for GSR, pulse, temperature, pressure, and altitude, parses it, and then appends this data to an Excel sheet. This script helps in creating data sets for model training and testing, enabling real-time data capture that's essential for model building and also for the machine learning accuracy. So now as we can see in this script that it has imported the necessary modules like serial, time, pandas, OS, and ARI. And then the serial configuration is done and we have an Excel file which is named as sensor values in normal life. So what it basically does is that its primary function is to collect real-time sensor readings, specifically the GSR, pulse, temperature, pressure, and altitude from an Arduino device via serial communication and log them into an Excel file. So the code first checks if an existing Excel file is present. If not, it creates a new one with appropriate column headers. Once the serial connection is established, the program sends a signal to the Arduino, prompting it to transmit sensor data. Incoming data is decoded and using regular expressions, 5 numeric values are extracted. These are parsed and appended to a pandas data frame and simultaneously saved into an Excel sheet. This module ensures that all physiological signals are logged consistently, providing a robust dataset for further analysis and machine learning processing. And now we are going to see the machine learning model which we developed. So it loads the dataset, performs pre-processing and feature scaling, and then trains a random forest classifier using label data. We visualize feature correlations using a heat map and pair plot, check model accuracy, and display the confusion matrix. The model is then saved along with the scalar label encoder and feature names for later use in live production. The model achieved high accuracy, showing its reliability for real-time stress classification. So now let's dive deep into how we actually built the machine learning model. So initially we have imported the important libraries and modules including pandas, matplotlib which is used for plotting the graph, seaborn which is also used for plotting the clustering graph, then sklearn model selection which is used for training and testing by first splitting the data into training and testing sets, and then we have the standard scaler and the label encoder for label encoding and scaling standardly. And then we have used the random forest classifier as our classification model, and for generating the metrics we have also ensured that we have imported important modules including classification report, confusion matrix, accuracy scores. So first of all, we have loaded the data and then put it into a data frame. So it begins by importing sensor data from an Excel file and performing exploratory data analysis including correlation heat maps and pair plots to identify the patterns and physiological signals. The target variable, that is the stress category, is label encoded for model compatibility. So as we can see, we have label encoded it for the compatibility of the model, and the data is then, and now we have also split the data into training and testing set, and features are standardized using this standard scaler as we can see. Then we have imported the model, and then we have put the data for training into the model, and then we have also started the prediction. So random forest classifier is trained on the data to classify the stress levels based on input features like GSR, pulse, and temperature. The model's performance is evaluated using classification metrics confusion matrix, and accuracy score. Also, the script visualizes the feature importance to identify which physiological factors contribute most to the stress classification. And finally, the trained model is also saved along with label encoder and scalar and feature names using joplib for real-time deployment and prediction pipeline, as can be seen here. So now let us also run the model and just see what things is it producing. Okay, so first of all, we have got this feature correlation heat map. So what it actually is. So basically, this heat map shows the correlation between physiological features like GSR, temperature, pressure, altitude, and pulse. Strong red, as we can see, 1.00, or blue shades indicate high correlation. For example, GSR and temperature have a strong positive correlation, while pressure is negatively correlated with altitude. This helps us understand relationships between features for better model performance. Next up, okay, so now we have this plot, which is a pair plot which is developed using Seaborn. So this pair plot shows relationships between all sensor features color-coded by normal and abnormal categories. We can clearly see how abnormal readings are clustering differently, especially in GSR and temperature, helping us visualize separate both conditions. And now we have the confusion matrix. So this confusion matrix shows perfect classification with just 41 abnormal and 125 normal instances were correctly identified with zero misclassifications, indicating 100% accuracy. Let's see what's next up. So next up we have the feature importances. So this bar chart highlights the GSR and temperatures as the most important features in stress detection, followed by pressure, altitude, and pulse with minimal impact. And we also have the metrics as mentioned here. This is the classification report, which has the precision, recall, F1 score, and support all mentioned here. Macro average, the weighted average, this is the confusion matrix we have the accuracy, and model is saved, label encoder is saved, scalar saved, feature names saved successfully as mentioned. Okay, so next up we have the terminal prediction. So this Python script basically reads sensor values from the Arduino and scales the input features. If the GSR is too low or the pulse is extremely high, the result is flagged as abnormal. Otherwise, the data is fed into the model, which predicts whether the current condition is normal or abnormal, and the result is printed on the console and also sent back to the Arduino to trigger the respective feedback mechanisms like the LED and the buzzer. So basically, what's happening in this code is that the script serves as a real-time prediction module, and it begins by loading the random forest model along with scalar, the label encoder, and the feature names as well. And then the system establishes a serial communication with the Arduino device. In a continuous loop, the code receives the live sensor readings, including GSR, pulse, temperature, pressure, and altitude, and these values are pre-processed to match the model's expected format using the label scalar. And if certain physiological thresholds are crossed, the system immediately flags the input as abnormal. Otherwise, it uses the machine learning. We can see it uses the machine learning model to classify the stress level, displaying the prediction to the user. And this module enables real-time decision making by integrating machine learning into live hardware input, ensuring a dynamic and responsive stress analysis system. And to make the system more interactive and user-friendly, I developed the graphical user interface using Tkinter and Matplotlib, and this GUI displays the real-time prediction along with live sensor data graphs for GSR, pulse, temperature, pressure, and altitude, as we can see here, as is mentioned here. So let's just run this and see what's going on. Okay, so we have this GUI based application right here. So if we click okay, so first let's see what all things are there. So there are two buttons, start and stop, for starting the prediction, stopping the prediction basically. And then also we have the live sensor data graphs for GSR, pulse. So let me just start the reading so that we can also see the development of the graphs simultaneously. So we have a GSR, we have a pulse data graph, we have a temperature, we have a pressure, we have the altitude. When the start button is pressed, the system begins communicating with the Arduino, reading values continuously and displaying them on scrolling plots. Simultaneously, it predicts the user's stress level using the trained random forest model, and the prediction is color-coded, green for normal and red for abnormal, to ensure immediate visual feedback. And based on the results, specific serial signals are sent back to the Arduino for further actions or alerts. This live dynamic interface not only enhances usability but also bridges real-time embedded systems with machine learning-based decision-making in an intuitive way. We can see that the prediction shown right up here is normal. Okay, so let us also try predicting the abnormal values. Okay, so right now we're simulating an environment in which, let's suppose, a person has some kind of stress. So let's see if we are able to achieve that. Okay, so now it's showing an abnormal prediction. Okay, so let us also see what's happening in the actual hardware. So now we are showing the working of the stress analysis system. So we have built a Tkinter-based GUI application. It will take some time. As we can see, the prediction is abnormal. We are trying to simulate a situation where a person can have stress. And then we'll see the red light, red LED and the buzzer being turned on because it's a abnormal situation where the person has high levels of stress.